All right, so then for chapter 8, the concept that we're going to talk about is this idea of momentum. So again, this is another word you probably use in your everyday life. We're going to put some more strict definitions to exactly what this means. So conceptually, the way you can think of this, this quantity of momentum is you can think of it as the more momentum an object has, the more difficult it is to stop, right? So if it has momentum, it's already moving. If it has zero momentum, then it is by definition not moving at all, right? So um, formally, though, the way that we're going to talk about momentum is going to be defined. We use the letter P for momentum. We're going to say it is a vector as well. It is the mass of an object times that object's velocity, right? So the direction is very important, right? So it will have some things that are kind of similar to energy, but it is a different concept altogether. And so we do need to make sure we understand what is similar and what is different. And one of the biggest differences is that momentum is a vector, so the direction is going to be very important. So it's actually a very fundamental quantity, so much so that you can write Newton's laws in terms of momentum, or at least certainly Newton's second law. And this is actually how Newton originally wrote this. So you can write the force on some object is actually equal to that object's change in momentum over time. So if you have some object and the momentum is in the process of changing, right, then you know that there is some sort of net force, or I should specify, there is some sort of net force acting on that object, right? So we have an object with momentum, right? It has some mass, it has some velocity. If either of these quantities change, obviously for our case, we're going to have mass stay constant for all the problems we do, but it can change. So for us, it would just be the velocity changing. So if you have some object moving along and the velocity changes, that of course is an acceleration, right? And as we know, F net equals ma, right? So we can actually write it like this. We can say m times delta v over delta t. What is m times delta v over delta t? Delta v over delta t is just a, right? So you can say this is also ma, right? So yeah, if we have an object and it has some sort of momentum, right, it's moving along. If it's moving faster, it has more momentum. If it's more massive, then it also has more momentum. And when you see that momentum changing, if there is some sort of change over time, right, you know that there's a net force being applied. And the faster it's changing, actually, right, if we have a large change of momentum in a very short time, then we can see that it is a very strong force being applied to this object, right? Or if you have a momentum changing, but it's changing very slowly, then you can say that it is a very weak force. But yeah, so we can actually also look at this idea of this term delta p here. It has a special name. It's called impulse. So the delta p is the change in momentum for some object, right? So you have some object, you apply a force to it, the momentum changes. That change in momentum is called impulse. And so we can solve for this very simply. We can say delta p equals F times delta t, right? So if you apply a force onto some object and you apply it for some amount of time, you will change that object's momentum, right? If you apply some sort of net force. And so there's a couple different ways you can do this as well, right? You can think of it like this idea of impulse. If you need to change your momentum, or if you need to stop some object, right, you need to change its momentum from whatever its value is now, right, in kilogram meters per second, and you need to bring it to a stop, right? You have to change the momentum, so you have to apply a force for some time, and you can either do that very quickly, right, if you apply a very strong force for a short time, or you can apply a weak force for a long time, right? But you can end up with the same change in momentum, right? So this is basically the same idea behind why airbags in cars are nice, right? If you get into an accident, obviously, you're driving along at say 30 miles an hour, your car runs into something, you're still moving forward, right? Hopefully, though, you hit the airbag, and then the airbag applies a weaker force for a longer time, right? You're in contact, you're pushing it into the airbag longer than you would if you just, hit your windshield or something like that. So when you have this idea here, right, like when you have a softer impact, right, I think you can just think of it like dropping like a ball or something. You can either drop it onto a concrete floor, or like drop it onto carpet, or like drop it onto a nice soft bed or something, right? In each case, it's coming to a stop, right? You're dropping it, it has some momentum, the momentum is changing. You're bringing that object to a stop, but depending on what it hits, right, we're applying a different force over a different amount of time. So like when you hit a nice soft surface or whatever, you apply a weaker force for a longer period of time to get the same change in momentum. Okay, so another reason we can talk about momentum, though, this is kind of one concept that we'll use, but something else. The main reason we use momentum, the most important thing about it is that momentum is conserved. So this is again similar to energy, but a little bit different because momentum is a vector, so we need to keep track of that. So what do you mean by momentum is conserved? So basically, anytime you have some sort of isolated system, right? You cannot create or destroy any momentum within it, right? You can add momentum to some system with some sort of external force or something like that. Um, but there's nothing you can do, right? Like just you pushing and pulling on yourself or something like that, to actually change the total momentum of some system, right? So you can actually look at it like this. So if you have two objects that collide or interact with one another, this is where this conservation of momentum becomes very, very helpful. So you can think of it like this. If we have, say, I don't know, we have two objects, right? We have object one goes this way. Say we have object two, and it goes this way, right? And they come together and they bounce off or they stick together or something like that. It doesn't really matter. However you think about it, we'll go over both types of collisions. So these two objects are coming together, they collide, they apply a force on one another, right? And so we'll call this object one, we'll call this object two. So we can say when they collide, right, they apply a force, so the momentum will change, right? So what is the impulse of object one? Delta P1 is going to be, well, the force on one times the amount of time that that object experiences that force, right? And so what's delta P2 going to be? The change in momentum of this one. This one's going to be whatever force this one experiences times however long that force is being applied. But we know some more things about this, right? Since they are interacting with one another, the simplest thing is to say this, right? We know that T1 has to equal T2, right? If they're interacting with one another, like if they're like bouncing off, they're colliding and pushing into each other and then bouncing off or something like that, they are interacting with each other for the same amount of time. So as long as this one is applying a force on this one is also going to be applying a force on this one, right? So that amount of time that they're interacting, right? It's not like P1 or it's not like object one is interacting with this for 3 seconds and this is somehow only interacting with this one for 2 seconds. That doesn't make any sense, right? They have to be interacting for the same amount of time. So the other thing that we know, right, about F1 and F2 from Newton's third law, if object 1 pushed on object 2 is going to push on object 1 with an equal in magnitude and opposite in direction force. So we know that F1 has to be equal to minus F2, right? So this object is going to apply a force on 2 to the right. Object 2 is going to apply a force on object 1 to the left. And those forces that they apply have to be related to one another, right? The magnitude has to be the same and the direction is different. So obviously then, if I take P1 and I add it up to delta P2, right? Take the two impulses, right? The momentum of object 1, this is going to change. The momentum of object 2, this is also going to change. But the total momentum of the system has to remain the same. So if I add up all the changes in momentum, we'd better get 0, right? So we're going to have F1 delta T minus F1 delta T, right? Nice and simple. Obviously, these cancel out. And so the overall change in momentum will be 0, right? So this allows us to write a very similar equation to what we had with our conservation of energy. Right? Our momentum in this case is being conserved. When we get to seeing some examples in later sections, we'll see why it's a little bit different again, largely because it's a vector quantity that we have to take care of, that we have to keep track of, and we have to conserve. But this does allow us to write a somewhat similar equation where we can say, okay, if two objects collide, we can have the momentum of object 1, right? So m1 v1, right? If some object comes in with some mass and some velocity, plus p2, right, of some other object that has a mass and velocity, has to be equal to p1 prime plus p2 prime. So what we're simply saying is the momentum before has to be equal to the momentum after, right? The change in momentum we know is going to be 0. So the momentum can move around. We can transfer it between objects, right? Again, you can have like a block sitting still, and then a block comes in, slides, hits it, and keeps going. This is like what happens with billiard balls a lot, right? If you're ever playing pool, right? The momentum is conserved, even though maybe it's transferred from one object to the next, right? As they collide with one another. So the momentum of each individual object can change, but the overall total momentum must remain the same. So yeah, so we can talk a little bit about some of the different types of collisions that we'll have. We'll wait till the next section to actually do examples. So one type of collisions that we're going to have would be this. We can have something called inelastic collisions. So these are a little bit easier to deal with, and the reason is because in these, momentum is conserved, as it always is, but kinetic energy is not conserved for these types of collisions, right? So in an inelastic collision, usually what this means is you have your two objects collide and then they stick together, right? For elastic collisions, elastic collisions are ones where objects tend to bounce off of one another. So for elastic collisions, we're going to say that kinetic energy is conserved. So that's kind of the main difference between the two, right? So for inelastic, so for both of them, momentum is conserved. For inelastic, kinetic energy is not conserved. This is in these collisions tend to be stickier, right? Where objects like stick together, right? And then move. Elastic collisions are bouncier, right? Where you have kinetic energy is conserved, where you have objects like come in and bounce off of one another, right? Is kind of how you can conceptually think of the two different ones. So for for the inelastic case, what would our equations be? For the inelastic case, it would be very simple. We could say this: if you have two objects, we'll say M1 comes in like this, M2 comes in like that. So again, with these, direction does matter, so make sure you pick a direction and are consistent with it. You can call M1 positive, you're moving in the positive direction. You can call M2 moving in the negative direction if you'd like, or you can switch them around, just as long as you're consistent about which direction is which. And so you would say is this, M1 V1 plus M2 V2 equals M1 plus M2 times V final, right? So this is my before picture for an inelastic collision. Let me make sure I label this. And then so then the after would look something like this. I don't know, depending on which one has more mass and which one is moving faster, right? Depending on what the overall momentums of these objects are. If object 1 has more momentum than object 2, right, and they collide and they stick together, then they will be moving off to the right this way. If object 2 has more momentum than the other, then they'll be moving to the left, right? But they'll each come in with some initial velocity. And if an inelastic case, they'll stick together, and then they'll move off in whichever direction of whichever object had more momentum. So the way I'm drawing this, this V2, you would plug in a negative number here, right, just to make sure to denote that this is moving to the left, right? And then afterwards, you can solve for this V final, and whether V final is positive or negative will tell you which direction this object was moving, right? So then for the elastic case, we have something that looks like this. This is my before, and then my after would be they have bounced off one another, right? So they came together, they collided, and then they bounced off. So they kind of came in and both connected and then went back from where they came, right? So this does make things a little bit more complicated, but we do have some more information at our disposal. Yeah, so again, we would have, right? So this is my equation for the inelastic case that I could pretty much use almost every time. For the elastic case, it's a little bit trickier. There's a lot more algebra that we can do, right? I don't have to give you as many variables, and it's because kinetic energy is conserved. So we actually have a couple different equations for this, right? So here we would say M1 V1 plus M2 V2 is equal to M1 V1 prime plus M2 V2 prime, right? So this would be one equation you could have. So already you have an extra variable right here. They're both moving together, so you only have the V final. Whereas here, they've bounced off, they're moving in separate directions, or not necessarily separate directions. They could actually be both moving in the same direction, again, depending upon the masses and initial velocities involved, right? If you have a very heavy object that comes in against a lighter object, they could both end up bouncing off to the right or both off to the left, depending on which one's which. But you do have separate velocities potentially for each of these objects, right? So in addition to this, though, we also can say 1/2 M1 v1 squared plus 1 half m2 v2 squared has to be equal to 1 half m1 v1 prime squared plus 1 half m2 v2 prime squared, right? So this is what it would look like for the case of an elastic collision, again, because for elastic collisions, kinetic energy is conserved. So this would be another equation that you would want to write. Maybe you can only use this one. Maybe you have enough information that you can just solve it from this one. But a lot of times for these elastic cases, it's a little bit trickier. I'll go through all the algebra with you and I'll kind of show you why it is. I'm not going to have you do this too much. I'll tell you this, I won't ask you the elastic case on an exam because it'll take you too long. But I'll show you some examples, and I'll have you do a homework problem where we actually do work all the way through this elastic case, right? So yeah, so these are our main types of collisions that we'll be dealing with. And so again, we are conserving momentum all the time, but kinetic energy is only conserved when you have this elastic case, right? In addition to this, we can also have collisions that occur in 2 dimensions. So how would that change the picture? Well, let's say we had 2 cars or something that collide right at an intersection. So you have car 1 that comes in like this. You have car 2 that comes in maybe like that, or at some other angle, depending on whatever it happens to be. But yeah, so when you have collisions that occur in 2 dimensions, you still conserve momentum, right? And it is a vector quantity, so that just means you have 2 conservation of momentum equations, right? You would say px1 plus px2, right, equals px1 final plus px2 final, something like that. And you would have py1 plus py2 equals py1 final plus py2 final, right? So essentially we're just saying we just now have another dimension to conserve momentum in, right? So we know if we have these cars here, then maybe if it's an inelastic or elastic, we're not really sure, but maybe they'll collide, maybe they'll stick together or something like that, and they'll move off at that direction, right? And so they would stick together, but they would both have, some sort of, there would be an x and y component to their velocities before and after. So you might write it like this. You just have to say m1 v1x plus m2 v2x equals m1 v1x prime plus m2 v2x prime m1 v1y plus m2 v2y equals m1 v1 y prime plus m2 v2y prime, right? Just to note that each velocity in this case is potentially a 2-dimensional velocity, right? And then of course, so this would be enough information if it were an inelastic case, right? And then you could just combine these, the final velocities would be the same as they stuck together. But if it were an elastic collision in 2 dimensions, right? Maybe you have, again, pool balls bouncing off one another is a very common example. Then in that case, you would still also have your conservation of kinetic energy equation. Oops, m2 v2 squared equals 1 half m1 v1 prime squared plus 1 half m2 v2 prime squared, right? But again, it's important to remember momentum is a vector, so we do have to worry about the 2 dimensions. Kinetic energy is a scalar, so we do not separate them. We don't break it down into x and y or anything like that. You would just use the overall total speed of each thing for this, right? So yeah, so we'll leave it at that for now, and then we'll see some examples and see some other different kinds of applications of momentum that we can do in our next section.